Laplace transform of the nth derivative of the function of the t is s to the n, oops, where did it go? S to the power n multiplied by the Laplace, remember from the lowercase f into the Laplace capital F, which is the function of the s, okay, minus s to the n minus 1 multiplied by the initial condition where f meant at for the f at 0 minus s to the n minus 2, the initial condition as the f prime at 0, and keep going. You see the order, the power of the s is decreasing. So n minus 1, n minus 2. So the next can be n minus 3. But the order of the initial condition starting from the f, next f prime, the next can be f double prime at 0. And keep going depends on the order n that you start with. So if you start with the n order, you're going to end up at the last one as s to the power 0, which is 1, multiplied by the last initial condition, which is fn minus 1 at 0. Okay, for example, for the Laplace of the first derivative, this is n equals 1, okay? This is n equals 1. So going to be s to the first multiplied by f, or the Laplace transform of the f of t, or the solution, minus s of 1 minus 0, 1 minus 1, sorry, it becomes 0. So 1 minus 1 multiplied by f as 0, and you stop right there. Or just s multiplied by f subtracted by the condition f0. This is n equals 1. For n equals 2, so the Laplace of the second derivative n2 is going to start with s squared. The Laplace f, okay, minus s of 2 minus 1, or s to the first, multiplied by the initial condition, subtracted by s to the power 0, which is 1, multiplied by the another initial condition. So we have s squared multiplied by f subtracted by s times f at 0 minus f prime at 0. For n equals 3, or the third derivative, so f triple prime at t going to be s to the third multiplied by the Laplace f minus the s to the second f at 0 minus s to the first f prime at 0, and the last one, no s or s to the power 0 minus f double prime at 0. Or we write it as s to the third f minus s squared f at 0 minus s f prime at 0, and then minus f double prime at 0. So we're going to use the transformation of the derivative as a substitution for the differential equation. Okay, and then for the homogeneous, we have nothing to worry about. We just work on the transformation of the derivatives for each order. But for the non-homogeneous, which is the right-hand side, is non-zero function, we're going to use the Laplace transform as the pattern that's we covered in 7.1. And the process to solve the differential equations, you do forward and you do backward. The first round, you're going to apply. So to solve, let me summarize this. Solve linear differential. Oh, what did I do? Hit the button. So linear, to solve the linear differential equation. Okay, so you're gonna treat it as the step 1. You're gonna apply the Laplace transform work with the linear differential equation with the coefficient as a constant term. Okay, as a constant term, and it has initial conditions. So initial conditions has to be part of the problem. Otherwise, but you can use a transform, but you cannot get to the end because the part of the transformation of the derivative, you're gonna use the conditions, the each one, the f at 0, f prime at 0, and so forth. Okay, step 1, you're gonna apply the Laplace transform to all terms. So step 1, step 2, just simplify algebraic term. Okay, after you apply the Laplace transform, so that means you start with the function in t, you're gonna get the function in s. So you have the simple algebraic terms as we use. Let me see. For example, if y is the solution that we are looking for, so then the Laplace of the y, we use the notation capital Y. Like the small f, we use the Laplace as the capital F. Okay, since the linear, the differential equation we are dealing with is y prime, y double prime, and so forth, or even the x prime, x double prime, something like that. So after you apply the Laplace transform, so you're gonna have the algebraic terms in the terms of the y, and the capital Y is the function in S. Okay, and then after you get the expression, you simplify and you solve for the capital Y. Okay, solve for capital Y. And the last step, you apply the inverse Laplace transform. So at this step, we're gonna do it backwards. So now, since the Laplace lowercase y is the uppercase y, so we do backwards. So the inverse of the capital Y is back to the lowercase y. So at this time, you're gonna get the y solution back as a function of the x or function of t. Okay, so y is the inverse of the capital Y. So kind of starting from doing forward, find the Laplace transform, simplify the algebra term, solve for the capital Y, and apply the inverse Laplace at the end. So that's why you you still have to look at 7.1. So now it's kind of combination of the two process in one. Okay, I'll do my best to explain slowly. All right, for the first example is y prime minus y equals 2 times cosine of phi t, where the initial condition y at 0 equals 0. As you see this, the y is the function of the t. Okay, put a note here. Y, which is y of t, is the solution that we are looking for. Okay, and when we apply the Laplace transform of the lower y, it's going to be the uppercase y. And the uppercase y is the function in S. And eventually, we're going to do the inverse of the capital Y to get back to the solution Y. Okay, so starting with apply the Laplace transform to all terms. So apply the Laplace transform of the whole thing. Y prime minus y equals 2 cosine 5t. And then the first one to be Laplace of the y prime minus the Laplace of the y equals 2 times the Laplace of the cosine of 5t. Okay. So for the Laplace of the derivative of the y, the n is 1. So from the theorem, this will becomes s to the power 1 of the Laplace of the lowercase y, which is the uppercase y, minus s to the power 0, okay, s to the power 0, multiplied by the initial condition y at 0. So these two terms is from the Laplace of the y prime. And then the Laplace of the y is the capital Y equals 2 times Laplace of cosine 5t. This is cosine of kt. And on the notes here, the Laplace of the cosine kt is cosine, you're going to have s as a numerator divided by s squared plus k squared. So this case, k is 5. So you're going to transform it to get s on the top divided by s squared plus 5 squared. Okay? This is the first step that we apply the Laplace transform term by term. And then from here, simplify a little bit. Now we have the s times the capital Y. S to the power 0 is 1. Y at 0 is 0 from given initial condition. So this equals 0. So this term is gone. That's nice. And then minus y here equals 2 times s divided by s squared plus 25. Now we have the algebraic expression in y, the capital Y. So this. In the y term. Okay, and next we're gonna solve for y. So I'm gonna go to the next one. Right. S capital Y minus y equals 2s over s squared plus 25 to solve for y. Factor the s out, factor the y out, so have s minus 1 multiplied by capital Y equals 2s divided by s squared plus 25. So then the capital Y is 2s divided by s minus 1 multiplied by s squared plus 25. Okay, we are done solving for y. In the next step, we are going to do the backwards, which is applying the inverse transform to y to get back to the solution. So y is the inverse Laplace of the capital Y, okay? But before we get back, we are going to simplify this expression, do the partial fraction